So today we're going to be reviewing the 2021 William Lowell Putnam Math Competition. We're doing problem A3. So we're finding where x squared plus y squared plus z squared is equal to n, such that we put a tetrahedron inside the sphere regarding that equation, where all four vertices of the tetrahedron are on that sphere, and we have to find n, or at least some form of n. So here we use points 1, 2, 3, and 4, and they have their own separate coordinates responding to their number, as in P1 is equal to X1, Y1, Z1, P2 is equal to X2, Y2, Z2, and so on and so forth. So, in order to find this n, we need to find the circumcenter and then circumradius. So, we try and find the center of the said tetrahedron and let it be X. Let it be like xn or something like that, such that distance between x1 and p1, x1 and p2, and x1 and p3 are all the same all the way to x1 p4. So I try to do it in this weird sine function way with regards to the angles of the triangles within the tetrahedron, but I said, nah, let's do barycentric coordinates. So instead of p1, p2, and p3, p4, we let them be lambda 1, lambda 2, lambda 3, lambda 4. So we're trying to find the circumcenter. We're trying to say that let the center U be the sum of the products of the points and the lambda barycentric coordinates from 1 to 4. And we already know that the sum of the barycentric coordinates is 1 anyways. So we let the lambda of I, as in the points, be equal to the radius over the height corresponding to the opposing area. As a result, we can easily derive that the height corresponding to the opposing area multiplied by said area is 3 times the volume. And therefore, we could turn this equation into this. As hi is the height to the corresponding area, we divide this by this to get hi, but because this is 1 over hi, actually, we invert them to get area of the corresponding height of the opposite plane, all divided by 3 times the volume multiplied by r here. So as a result, this center U, this lambda I is replaced with a constant 3 r over 3v multiplied by the sum of I equals 1 to 4 of the area, corresponding area, which is equal to 1. As this is so implicated here, we can easily then verify into this sum, this fraction over here, the sum of I equals 1 to 4 of the radius of the area multiplied by the opposite point, divided by the sum of all the areas of the thing. So this is basically this is it. As in, this is the center of it. In even more simplified form. So, in order to find this n specifically, though, we need to find this Cayley-Manger matrix for the circumradius. We need to know what that is. So, we have to understand that the Cayley-Manger matrix, is this matrix, this is meant to be D, so this is meant to be this D matrix with entries I and K, with vertices all the way for 1 and 1 all the way to j plus 1 for a jth order simplex, basically. So because we're doing the tetrahedron with 4 vertices, it is what we call a 3 simplex. So j would be 3 in this manner. So we're defining the entries of this D of ik. We would be with the distances of the vertices between each other squared. So it's a squared distances. So if we want to even go even further, we can even go as far to say that the Cayley-Manger matrix for an order j squared is going to be the determinant of the j plus 2 matrix multiplied by -1 to the j plus I divided by 2j to the power j multiplied by j factorial or squared. So you may need to know, why is this important in this case? Why? So it's a really weird derivation we need to start with from a man named Miroslav Fiedler in the book Matrices in Geometry. So we said let the Gramian be like some q. Let it be some q of the set of the vertices from I equals 1 all the way to n plus 1. We assume that, and we saw that this is the zeroth order of the Gramian of q0, 0, q0 transposition, so forth, and m0. M0 is going to be our matrix, going to be our Gramian matrix. So as you can see here, we can say that q entries are defined by qi and k of the vertices all the way from 1 to n plus 1. And then we can say that the sum of sums of the m entries from here and q entries from here is equal to minus 2 times delta s of t. I said this is some identity in the book in and of itself that honestly, because it's a part-time problem, we'd only have like 30 minutes to solve, I think. No, not 30 minutes. We would have a certain limit of time. We would have to derive that one, and that would become very complicated quickly. So we assume that this is a Q-tundle. This is a Q-tundle, as in this is the variance of the Gramian. As in, instead of going from I equals 1 all the way to m plus 1, it's I equals 1 all the way to m. And it's the same thing for m here. However, it says that we use this coordinate, we are trying to find the distances between these two, right? And even then, that's also from I to n. So in order to find the product instead of the bracket of this ci minus cj, it's basically like expanding something like a plus b squared or a minus b squared, except it's using this bracket notation. So it's ci minus 2ci and cj plus cj. Like, it's very, very similar to the squaring a minus b squared. And we even could then go on to say that as a result of this, the result of this bracket notation is a function is equal to 1/2 times m being one of the m entries from here, m of e tundle t coming from here as well, e tundle transposition t minus the tundle of e m transposition t minus the transposition of the m matrix in general, such that the e tundle is just a line matrix from 1 to 1 transpositioned. As a result, we try to find that m tundle and q tundle is equal to minus 2 times I of n. This is also another identity in the book as well, which is just assume minus 2 times I of n plus m times the transposition of e tundle t times the tundle of q of the Gramian plus the tundle of e times m to the m transposition t times the Gramian of q. So we find that this q0 is just another identity as in lambda q, as in gamma q, and that goes on to like q equals minus the tundle of the Gramian multiplied by the m entry of the m0. And then we can even go further, expand it, as in this is basically just a construction that's when applied, as into this formula over here, we get minus 2 times I n plus 2. As in that n equals minus 2, we find that m0 times q0 equals to minus 2i, where I is the identity matrix. So we can easily say that q is equal to minus 2 times m times the inverse of m0, as in you'd even get this as a result. So in order to go ahead and prove whatever this q is, as in the radius, the circle radius, we have to use Sylvester's identity, where the determinant of one matrix times the determinant of another variant of a matrix times position to a position u of variant v to the power of n minus 1 is equal to the determinant of a matrix A with tundle U with variant V. So the book goes on to propose that minus 1/2 of Q of II is equal to that the determinant of the M0 order of I divided by M0. So we learn in this equation by Ivanov. So Vladimir Ivanov proposed this equation in like some 1970s US magazine, which was used in the derivation of the circumradius, where where v squared, with the volume squared of the sum of volume squared of a certain sum of a certain order, let's say let it be n, would be minus 1 to the power of n plus 1 divided by 2 to the n times m factorial squared multiplied by det of mo, as in the determinants of the M matrix. So as a result, we rearrange for det of mo to equal this. And then we allow, and then also there's another equation that appears in the book as well. That is the full one, as in the volume squared of the sum of some identity I is equal to minus 1 to the s times 2 to the s minus 1 multiplied by s minus 1 factorial all squared times the determinants of m0 of I, as in s is the order simplex that we need. As a result, we therefore again we rearrange for the determinants of m0 of I. And as a result of this expansion, here, we get this, right? We get this as a result. And from here, we'd easily go ahead and say that this, when terms cancel out, we get the volume squared of n minus 1 from lambda 1 all the way to lambda n plus 1 divided by n squared times the volume squared of a certain simplex n of lambda 1 is all go to n plus 1. Because we're assuming that this is the third order simplex as a tetrahedron, we assume that n equals 3. So we then go on to prove the fact that negative 2r squared is equal to determinant of m divided by determinant of m0. So as a result, we then go on to say this. We then go on to say the fact that minus 1/2 of qii is equal to determinant of m0 of order I divided by determinant of m0 is equal to minus 2r squared. So as halves qii is equal to 2r squared, qii is equal to 4r squared, and qii over 4 is equal to r squared, we'd say that n is equal to r squared, as in this is the final thing we need to do, and this qii divided by 4. But the thing is that this question specifically mentioned that all vertices should be integers. So if we actually go back to an original form of this, we'd be able to find, as the fact that we use 288, as 288 is equal to 12 squared times 2. And as a result, we would find that 200 qii is going to be some 12k squared. So as 2a is equal to 12 squared times 2, we would assume that it's going to be like 12 squared times k squared all the way to so on and so forth. And as a result, as qii is equal to 12k squared, 12k squared divided by 4 is equal to 3k squared. So in order for all the vertices on the tetrahedron to all be on the circle, and for them all to be by eccentric coordinates of positive integers or integers in general, n would have to be, as in r squared, would have to be some form of 3 times some other square number. So 3k squared, basically. So one of my reasons why this is my most favorite part 9 problem ever is simply because it has direct implications on the research that I'm doing, as in regards to orbital flight paths. So just for a little bit of a stint, my research involves making a tetrahedron of the L points and trying to find the centroid of that, and then